Mark P. Otten back with you. All right, welcome to your structural equation modeling in R video, or your first one at least. This video builds on your path analysis in R video and your confirmatory factor analysis in R video. In fact, if you put a confirmatory factor analysis together with a path analysis, you have a SEM, structural equation model. And that's what this is here. In your notes, I'm going to try to run this model with cognitive anxiety, self-confidence, and somatic anxiety latent variables, all predicting basketball performance, another latent variable, and in particular try to get these numbers. This is from your SEM video where I take you through these slides and what this all means. Okay, so on the left we have R. I have imported some data, imported this, in fact, this particular data set. And I've remembered to select Levon on the right side here as the package that we need to run this SEM. My data looks like this. Another thing I recommended in one of the videos, maybe all of my videos, I recommend this. I can't remember. I like to do this, and that is clean out my data set first before importing it into R. In particular, eliminate all variables from the data set in SPSS that are not in your SEM before running it, because I feel like when you pull it into R, it just, like we're going to run a covariance matrix here. It only runs the covariance matrix for the variables in your model as opposed to including extras. So anyway, I like to keep things as clean as possible if I can. This is the 9 PCA, what is that? PCSAI. That's like a post competitive state anxiety inventory measure, 1 through 9, and then a basketball performance measure here 3 different ways toward the end. So 12 variables. I have called my data set Light the Beam in honor of the Sacramento Kings and my favorite team. That's their slogan. Don't worry about it. Anyway, okay, so in R we've got the code over here on the left, and I am starting out by designating our latent variables, and then I'm going into the regression below that as all part of the SEM. So I started it out by calling it basketball. This is a basketball model, so that I just called it that. You can call your model whatever you want. And then you've got this little arrow pointing to the name of the model, and then you've got the single quote here or apostrophe starting the model, and then you've got all your statements in between. You've got cognitive anxiety, in this case, equals tilde. That's designating cognitive anxiety as a latent variable with the components here, 2, 5, and 8 from the scale, V2, V5, V8 in the diagram. And then similarly for confidence and similarly for somatic anxiety, which I designated as SOM anxiety, you've got those all 3 specified there, 3 latent variables, each with 3 components. The fourth line here is your DV, also a latent variable, also with 3 components. That's performance in this case. And then your last line here is your regression performance, tilde without the equals. And then that means that performance is being predicted by 3 IVs, and then your 3 latent variables specified there. So I do it in that order because I specify the latent variables first, and then in the regression, once you get to the regression, R will know that those are latent variables and how they are specified in this way when it gets to that line, and it will know what to do. So in this case, 4 latent variables, so 4 lines of code there, and then a 5th line designated in the regression. You do not have to declare the correlations. There's correlations between the IVs here as part of the model, right? F1, F2, F3, all are correlated. By default, R will correlate them for you. The only thing you have to think about is if you don't want them to correlate as part of the model, then you have to tell R not to correlate them. But since they're correlated here, we're going to let R do its thing. The next couple of lines here are just to specify the model, which is something, if you've watched my other videos, you might have seen something similar. Basketball.fit, so you just call it, it's the name of the model, .fit equals SEM, parentheses, the name of the model again, and then the data set, name of the data set there. Summary, parentheses, that line is going to give you all your standardized values, your fit statistics, and so on. So we can start with that. Let's do that first and run it and see if the numbers match up. Okay, so you've got them all here in the lower left. By now you might be running, you might have found another way to display your output in a more fun way. I don't know. For me, I try to keep it simple here. So this is the simplest way to show you your output, I feel. And so where are these values? Okay, so the latent variable section here and it is partway down the output. And you've got the std.all column, which is the rightmost column. That's where your standardized values are. And you can see the factor loadings going down 0.81, 0.85, and 0.81 for factor 1, cognitive anxiety, and so on. We've got this strange factor loading, by the way, in this model, 1.04. That is technically possible. Basically, that performance latent variable it's essentially the same as V10. And we could theoretically drop that 0.00 residual variance out on the side there, but I'm keeping it in. I'm trying to keep this simple for you guys. So we'll get to that here again at the end when we're talking about post hoc modifications. But for now, we're just looking for these values. So all of the standardized values are here. Those are your factor loadings in the latent variable section on the far right. The regressions come next. Again, you look at the far right column. You've got the 0.24. That's F1 with F4, cognitive anxiety and performance. 0.462 is your confidence performance relationship. And at this point, I should note, hey, wait a minute, what about significance? Okay, so going back to the factor loadings, you look at this P greater than Z column, lots of zeros. All of our factor loadings have p-values associated with them that are less than 0.05. Thus, all of them are significant, at least the ones that are tested. The first item from each factor, you see there's no p-value there. There's no significance test for the ones that were designated as 1 initially as part of our iterative process. The factor loading was set to 1. So there's no significance test there. So therefore, I didn't include stars in the diagram that correspond to those particular factor loadings, but all of these others have stars and the p-values are less than 0.05. However, for the regressions, we've only got 1 out of 3 that has a significant beta. This 0.46 has a p-value for p-value 0.00. That's confidence and performance. The other 2 have p-values of 0.17 and 0.36, non-significant, which has implications for whether they should remain in the model at all. So take a look at that p-value column as you're going along and finding your values for your model. The covariance section here, if you go to the far right, those are your correlations. Your negative 0.35 is F1 and F2 and so on. Those are all significant here with p-values less than 0.05. And then the variances section, if you go to the far right, those are your residual variances out on the side. So the 0.34, that's for V2 here. 0.28 or 0.275 here for V5 and so on from, again, this std.all column. And they all get significance values, stars to denote significance, except for that one weird performance 1 V10 value here, which is not significant. So, okay, so that's the basics there. That's your model with all of its values found. If you get stuck at any point trying to find one of these various values in there and you can't find it, just let me know. The rest of the code that I'm giving you for this particular video is the supplemental stuff. So the first thing is the section here where I'm allowing you to get your covariance matrices. So this first line here is fitted parentheses, name of your model, dot fit. That one is going to give you your covariance matrix that is implied by the model. So you got all of your measured variables here with covariances laid out. And then you've got the next line here, which is your covariance matrix that comes directly out of your data set. So it's going to be the same variables. This one looks a little bit more annoying because it's got the top half of the diagonal in addition to the bottom half of the diagonal, but those numbers are redundant with each other. So you can look, for example, at this 0.812, that's a variance for the V2. And then you can go to, that's implied by your model. And then you go to the variance for V2 here in your actual data is 0.82. So it's close. So you can match that up, or that would be sort of eyeballing it. Or you can just go to the residual matrix. The residual matrix will subtract every single covariance from your model from covariance from your data, thus comparing them in one swoop. So this is that residual matrix. So these 3 lines of code are for your covariance matrix implied by your model, your actual data covariance matrix, and then the residuals, or each value subtracted from each matrix. So run that, print it out. No need to interpret too much because the interpretation comes from the fit statistics, which we will also talk about. I skipped those in the main output, but we'll come back to that in a second. Actually, let's talk about that now. Let's talk about that now. Okay, let's scroll back up. Okay, so your default for R is to run maximum likelihood as your estimation method, or the method behind the madness here. And so if you go up to model test user model, that is R's strange designation for your chi-square test, which comes out to be a 90.41 here and a 0.00 p-value, a rejection with 48 degrees of freedom. The chi-square test does not like this model. However, if you go to the comparative fit index, 0.965, that's pretty strong. It's actually very strong. And the RMSEA is 0.067, which is also pretty strong. So that's where you find your fit statistics. And we'll find a couple more in a second. Okay, let's talk about modification indices or post hoc tests next. This is just one line to give you the LM test, Lagrange multiplier test, which allows you to sort through your data set and look for paths that could be added, or if added to the model, would make your model stronger, would strengthen the chi-square test statistic. So if we run that, you're going to get a long list. In fact, it's so much, you're like, did anything just happen? Yes, it happened, and it's just this really long list of stuff here. So in my video on the theory and what this all means in terms of post hoc tests, I talk about 3.84. 3.84 is your chi-square test 1 degree of freedom critical value. If these values in the MI column, this is your MI column, modification index, if these values are greater than 3.84, then if you add the path, it's going to help the model. It's going to help your chi-square by the amount that's listed here. So for example, this first line is proposing that basketball performance 2 become a element of the cognitive anxiety latent variable. That's what this is denoting here. Cognitive anxiety on the left, that's your latent variable, equals tilde, implying that performance 2, the value on the variable on the right, should be equals tilde, part of that latent variable. So if we were to include, which doesn't make any sense, by the way, basketball performance should not be part of anxiety. I'm just telling you that. But if we were to add it to the model, the chi-square test would improve by 12.745, and that value 12.745 is greater than 3.84, which is your cutoff point for value in this case. So it would improve the fit of the model. However, it doesn't make theoretical sense. So we're not going to do it. And that's the where the scientific method should come into your brain and at each decision point here be like, okay, that will statistically improve the model, but does it make sense? In this case, no. And like, you should be honest with that. Like, try not to make stuff up. Oh yeah, that makes sense because of blah blah blah. Like, if you're sticking to the scientific method and your theory and your original model, then you're probably not adding these values very freely. So, okay. However, when we go down the list here, man, there's quite a few that are above 3.84, like all the way down to this one. See, where it's like 3.277, that's below 3.84. This one's 3.89. So there's a whole bunch. There's like 15 possible additions there. And so theoretically then you should go down and, okay, that first one didn't make sense, reject that one. Okay, go to the next one. Does that one make sense? And go step by step through each one that's suggested to see if any of them make sense. Now, for our model, we've kind of maxed out. Like, this is already a foregone conclusion in a way, because like, I'm not going to, okay, we have cognitive and somatic anxiety here, and they are separate latent variables. So like, some of these suggestions might be to include somatic anxiety variables on the cognitive anxiety latent variable and vice versa, right? Cross loadings there. But the cognitive anxiety latent variable is already correlated with the somatic anxiety variable as 0.84. Like I'm already acknowledging through this model that those things are related to each other. So I don't need to have the variables then cross load onto each other's latent variables, because then that's like a duplicate almost of the representation of the fact that those two forms of anxiety are already related. So I'm already, like, before even running this series of post-hoc tests, I'm already going to tell you that none of the additions are going to make sense. And you can kind of decide that at any point in the process, again, based on your theory, based on your expectations to going into the modeling process. So I'm showing you this because a lot of these values, a lot of these relationships between variables would improve the model, but we're not going to add them because they don't make theoretical sense in this case. Okay, so that's the process. Again, let me know if you have questions as you go through this in your homework or your own research. A couple more things to show you real quick. One is the decision regarding the Wald test. So the Wald test is the other modification, post-hoc modification to consider. And the Wald test is not actually being run here, as I note in the other video where I'm talking about the Wald test. Our computer program does not run it for you. At least I don't know. I haven't done it before in R. But what we should do is we should look through these different relationships that exist in our model and see if any of them are non-significant. And sure enough, in this case, we have a couple of non-significant relationships here. One between F3 and F4, somatic anxiety, non-significant predictor of performance. And then the other one, cognitive anxiety, similarly, non-significant predictor of performance. So what we should do is we should go back and we should drop somatic anxiety from F4, performance. We should drop it from the model and then see what happens to our chi-square test. So I'm not going to do that here because I want to just keep things simple in the video, but I'll show you what I would do if I were to do it. So you see somatic anxiety here is a predictor of performance as part of the regression there. So you would just delete that and just have performance be predicted by cognitive anxiety and confidence only. And then everything would change. The degrees of freedom in the model would change by 1, and you could look at the chi-square before and after that change to see what happens. And if that change causes the chi-square value to change by more than 3.84, again, that's that cutoff point, then that's a significant change to the model by dropping somatic anxiety, and we probably shouldn't do it. We're changing the model too much. Dropping that path made a difference, so it should be in there. However, if we do that and the chi-square doesn't change much, doesn't change more than 3.84 in value, then dropping somatic anxiety didn't really matter. So let's drop it. Let's make our model smaller and more straight to the point. And if that were the case, then we drop it successfully, and then we go look at F1's relationship with F4, cognitive anxiety. Maybe now performance is only predicted by confidence, and that's it. Again, drop one, check the results. If you're approved, if the numbers tell you to keep going, drop the next one. If we were to drop both of those, then we're kind of out of options because there's no more non-significant paths here to drop. And so you probably stop there. So in this case, you wouldn't drop more than 2 paths because there's not more than 2 non-significant paths to drop. Okay, so that's the general process here. Again, I'm not dropping and recalculating for you, but in your homework or in your research, if you were dropping things, that would be the kind of the iterative process, both for adding and for dropping. Okay, finally, we have a fit measures statement in addition here that's going to allow us to get a couple more fit statistics. I'm just going to run this really quick and show it to you. This is the NFI and the GFI, and there's other fit statistics that are out there that you might want to get. And so you can look this code up for other additional fit statistics. But for our purposes, it's just going to give us one line with those values. And then the other one that I didn't talk about earlier was the SRMR, which is actually present in our original output. If I scroll way back up here, you've got the standardized root mean square residual there, 0.063. So a couple of additional fit statistics for you and then that one which I skipped over originally. And then the last thing to show you in this video is something that I'm also not going to run, but I wanted to show you anyway. And that is what happens if one of your variables, in particular your dependent variable in your model, is a ordinal variable. This is how you tell R to treat it as an ordinal variable and allow R to recalculate things accordingly. So this is just a statement that would go, let's see, originally we had this one here, which is your initial statement to tell R to start running an SEM. And so if your dependent variable in this case was, or actually any variable, but if your dependent variable is ordered or ordinal, then you take this line and you just replace this one, line 9, with line 20 here. And then the quote variable name, that's just whatever variable is in your data set that's ordinal, call it that. That's where you put the name of that variable. So that's all that would change. Then everything else that you would normally do for an SEM, once you replace this line or add that little section to that line, everything else will unfold the same way. The code is all the same. So, okay, that's your introduction to a full structural equation model in R. I hope that was helpful.